Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Tonight we're very honoured to be joined by John Lewis, who is a Professor Emeritus at the University of Arizona. John did his a BS in chemistry at Princeton, and then an MA in inorganic chemistry at Dartmouth, before he moved to the West Coast and worked with Harold Urey at UC San Diego. He did his PhD in geochemistry and cosmochemistry. John then taught for a few years at Space Sciences and Cosmochemistry at MIT. Before in 1981 he moved across to the Lunar and Planetary Laboratory at University of Arizona, where he's taught ever since. And many of his students make up the planetary sciences community today. John has published several books, including with such titles as Planets and Their Atmospheres, the 1997 book Mining the Sky, The Reign of Iron and Ice, and the 1998 book Worlds Without End. He is also the editor of the Science, edited the Resources of Near-Earth Space in 1993 as part of a University of Arizona book series. His career has revolved around the composition of asteroids, chemistry and formation of the solar system, and the economic development of near-Earth space. He's also the chief scientist of a new firm called Deep Space Industries. And I'm sure we're going to hear a little bit about that in his talk tonight. So if you'll join me in welcoming John.
Tonight we're going to tour quite a bit of countryside. We're going to cover a lot of ground and a lot of intervening empty space as well. And the challenge before you all is to think in terms of that little object floating there in the upper right-hand corner of the screen. That's an asteroid, more or less a small asteroid, more or less to scale with some mountains. We are going to be talking about gaining access to nearby asteroids, and then what that gives us in return for our efforts. The challenge is to think outside the box. This photograph was taken by the Galileo spacecraft on its way out to Jupiter, looking back over its shoulder, so to speak, at the Earth-Moon system. The Earth and the Moon, very simple, isolated little islands in space. But we shouldn't limit our vision to just this small system, especially since we have many objects that visit our system and actually pass closer to the moon than the moon quite regularly, quite frequently. They're called near-Earth asteroids. What is a near-Earth asteroid? It's any asteroid that approaches within 0.3 astronomical units, which is about 45 million kilometers of the Earth. Many of them in the past have passed inside the moon's orbit. Many have struck Earth. There are nearly 200 documented impact craters on Earth, most of which were produced by near-Earth asteroids. And they are the immediate source of the large majority of the meteorites that fall on Earth. It means that we have in our meteorite collections samples of many, many different asteroids. What can we learn from the study of those meteorites that help us to understand the asteroids and that prepare us for actually going to those asteroids and trying to use them? The near-Earth asteroids, as attested by the meteorites, have a huge range of compositions, a great variation in their chemical composition and strength. And discovering them has been a cottage industry for some years now. The very first near-Earth asteroid was actually discovered in 1898, although the possibility that cosmic bodies could collide with Earth actually goes back quite a bit farther to Sir Isaac Newton. The first systematic search for near-Earth asteroids was conducted by Tom Gehrels, starting in about 1960, where he discovered several asteroids, some of them with very interesting orbits, one going as far out as Saturn. And then he initiated the Space Watch program at the University of Arizona in 1985. my book, Rain of Iron and Ice, the rules are that I don't have it with me, but believe me, it exists. You don't have to read it, but you must buy a copy. Okay. Published. No, no, they're trying to, Dave asks, is it still in print? They're trying to coerce me into updating it. Unfortunately, that's what happens when you write a book. You just, and then the large efforts to find near-Earth asteroids became part of NASA's program starting in about 1997. If you infer a cause and effect relationship between the 1995 and 1997 entries here, I'm flattered, but I can't really claim that it was all my fault. Here's the rate of near-Earth asteroid discoveries. Now you see these numbers up here around 500. These are on 6-month bases. So it's 500 asteroids every half year. And you see back in 1997, when the Linear program at Lincoln Labs came online, the discovery rate accelerated. The NEAT program came and has faded down to a very low discovery rate. Space Watch went through an early, very successful phase. Then a second generation Space Watch telescope came in and it was revived. Nowadays, Space Watch mostly does follow-up rather than original discovery of asteroids. The LONIOS program also came and faded. The Catalina program, also housed at the Lunar and Planetary Lab at the University of Arizona, has been extremely successful. And the Pan-STARRS more recently, another search program. And then all the others combined, I have just included in here as white. There are many individuals who have discovered asteroids, including everybody from Maximilian Wolf on down probably to my grandchildren. But they all get lumped together. So this is what the discovery rate looks like, about 1,000 new near-Earth asteroids per year. This is what their orbits look like. To calibrate you on here, this is the orbit of Mercury here, the orbit of Venus here, the orbit of Earth right here, and the orbit of Mars here. Why are there so many near-Earth asteroids so close to Earth? Because that's where we live, and that's where we're observing from. So many of these asteroids that are very close to Earth would not have been detected if we lived on Venus, because they'd be too far away, too small, too faint. So don't get paranoid about this, or don't get overly paranoid about it. It's good to cultivate a little paranoia when it's realistic paranoia. So of this swarm of near-Earth asteroids, roughly 30% of them eventually, in the long run, are going to collide with Earth. Now, if this is a 7, 8, 9, 10 meter diameter object, you can probably shrug it off and say, oh, that was spectacular, or that was deafening, or that broke my windows. But if it's a 1 kilometer sized object, it could ruin your entire day and the following weekend. So how many near-Earth asteroids are there? The near-Earth asteroid population is variously estimated at numbers between 920 and 1,010 or thereabouts. I'll just say in round numbers, 1,000 near-Earth asteroids larger than 1 kilometer in diameter. A 1 kilometer asteroid is a significant piece of rock. You would not want to meet one in a dark alley. There are roughly 200,000 near-Earth asteroids larger than 100 meters in size. And 100 meters is roughly the fuzzy borderline between those which are spectacularly visible and maybe acoustically deafening but survivable, and those that are so large that they represent a serious hazard to anyone who's living on the ground under them. That size is often quoted as 140 meters. The error bars on that, due to the known variation in strengths of meteorites and asteroids, are huge. So don't take that number too seriously. Have you all turned off your cell phones? That's never happened before. Probably a solicitation. Their orbital periods mostly range from about 0.9 years to about 7 years. Their orbital inclinations are typically 10 to 20 degrees, although there's quite a wide range from 0 up to over 40. How did you get past my security? Thank you. Their orbital inclinations, 10 to 20 degrees, mean that they lie fairly close to the plane of the orbits of the planets, but not too close. If you look at the distribution of their orbital inclinations, those that are inclined less than 1 degree or so to the plane of the mean plane of the solar system are severely underrepresented. And the reason is very simple. If they're essentially in the plane of the terrestrial planets, they don't last long. They are, to use the technical language of theoretical astronomy, playing on the freeway. They will cross the orbits of the terrestrial planets in the same plane as those planets, and they have a high probability of getting swept up. Some such bodies have expected orbital lifetimes of only 10,000 years, but the main bulk of the near-Earth asteroid population typically lasts about 30 million years. So you see there's quite a difference. The eccentricities of their orbit, the degree to which their orbit departs from circularity, ranges widely from essentially 0 up to about 0.9. A 0 eccentricity, a circular orbit, puts it in the same category as, say, Venus or Earth, very, very planetary, and very little opportunity for crossing the orbits of other planets. And an eccentricity of 0.9 is an extremely elongated orbit, which we would otherwise call a cometary orbit. So a good question would be, how many of the near-Earth asteroids may simply be hibernating or retired near-Earth asteroid comets? Near-Earth comets masquerading as near-Earth asteroids, okay? Most eccentricities are in the middle range, around 0.4, 0.5. Most near-Earth asteroids pass through the asteroid belt on each trip around the sun. There have been a number of missions which have been planned in the past to take advantage of the existence of asteroids to justify getting money from the legislatures of various countries to send missions to them. Galileo flew by the asteroid Gaspra on the way to Jupiter. The Vesta mission, which you've probably not heard about, was canceled before it flew, and that's why you haven't heard about it. But it was an ambitious plan, in some ways similar to the present NASA Dawn mission, to go out and orbit the asteroid Vesta. Galileo flew by Ida, the NEAR mission, Near-Earth Asteroid Rendezvous mission, Cassini. Cassini flew by a friend of mine in the year 2000. NEAR landed on the asteroid Eros in 2001. Hayabusa was an attempted sample return whose retrieval mechanism failed, but it succeeded anyhow because it came back and landed on Earth and some dirt was found on it, which came from the asteroid. Rosetta flew, it's a mission, it's flown by 2 asteroids, and it's on its way to orbit the comet Churyumov-Gerasimenko in 2014, and then land on it. And the Chang'e mission, which was a lunar orbiting surveying mission, was then moved out to the lunar L2 point, I guess, and stored there for a while, and then dispatched from there on an intercept to fly by the asteroid Tutatis in 2013. Tutatis being an asteroid with a notoriously unstable orbit, which is a potential threat to Earth. Then we have the Dawn mission, which is in flight. It has just completed a year's survey of Vesta and is now en route to Ceres, where it will arrive in a couple of years. So there's been a lot of spacecraft information about asteroids, but even so, there's that completely unrelated body of data on them, which we get from the study of meteorites, that needs to be integrated with the spacecraft data in order to understand. That is so impolite. So I'm going to be talking, among other things, I've mentioned the hazard due to near-Earth asteroids, a subject dear to my heart, or I wouldn't have written Rain of Iron and Ice. And I'm going to be talking a great deal more about the economic desirability of the near-Earth asteroids, talking about them as bodies which carry resources, which may be of use to humanity. We'll be talking about several aspects of making them desirable to us. One is that they have to be easy to reach. One is that they have to be easy to get back from to the place where you want to deliver the resources. Third is that they have to have a decent abundance of useful and interesting ores. And an ore is not just a mineral or a rock. An ore is something which can be dug, processed, marketed, and sold for a profit. And finally, we need to have simple, efficient processing schemes to get from the raw rock to a marketable product. So we'll be going over those over the next 4 slides. Now, easy access, we usually think in terms of the space station as being the base from which we depart to go outward. It doesn't have to be the ISS, but any low Earth orbit space station. Low Earth orbit, LEO, not the constellation LEO, low Earth orbit, is at a typical altitude of 400 to 600 kilometers. Easy access to the near-Earth asteroid from LEO means that the velocity that you must impart to the spacecraft to get to the asteroid, the delta V, the change in velocity, is small. How small? Well, we'll talk about that. Then the total delta V from low Earth orbit to landing on the asteroid must be greater than about 3.2 kilometers per second. Why? Because they're outside Earth's gravity well, and you need 3.2 kilometers per second to get out of Earth's gravity well. And should be less than about 6 kilometers per second, which is the delta V required for from a typical launch site on Earth, going through Earth orbit to the moon to land. So a lunar landing requires 6 kilometers per second, and we'll try to limit ourselves to asteroids that are more accessible outbound than the moon itself. There are such asteroids. You may not have known this. If you haven't worked the numbers, you probably don't know this. But in terms of the energy requirement to get from low Earth orbit to the surface of a moon, our moon is not the most accessible natural satellite in the solar system. There are 2 others that are easier to get to. The 2 moons of Mars, Phobos and Deimos. Strange. Okay, easy return to low Earth orbit or to the vicinity of Earth means that the delta V, the velocity change requirement, must be, from the asteroid, must be low. And this is extremely important. It's even more important than the outbound delta V because on the way back, you're going to be carrying a lot of weight. So the cost of moving that weight must be kept as small as possible. Return to a highly eccentric Earth orbit. That's one which grazes the top of the atmosphere and may go out 1/10 of the way or all the way to the moon at apogee. Return to a highly eccentric Earth orbit is easier than return to low Earth orbit. It requires less energy to be dissipated, smaller velocity change. And highly eccentric Earth orbit's actually a very good base of operations for outbound missions to the moon or to Mars or to anywhere else in the solar system. Return delta V's, the velocity increment required to get from the surface of near-Earth asteroids back to intercepting Earth's atmosphere, are in some cases less than 60 meters per second. These have been documented for several near-Earth asteroids. Returning from the moon requires not 60 meters per second, but 2,600 meters per second. And if you're talking about carrying mass, retrieving mass, it should be clear that the near-Earth asteroids offer enormous advantages over the retrieval of lunar material. What useful materials might we expect to find on near-Earth asteroids based on our experience with both spacecraft missions and meteorite studies? Okay, we have here water as the most important single ingredient of asteroids. Why is water important? Water is the raw material of propellants. And propellants are what allows you to move whatever you want from wherever it is to wherever you want it. So propellants that can be derived from the asteroid impart huge leverage. The C, D, and P asteroids have 1 to at least 20% water. Extinct near-Earth asteroid comet cores may be up to 60% water ice at depth. Here's what happens. You know, a comet is a dirty snowball. It's mostly ices, and dirt. When a short period comet passes through the inner solar system, it is blasted by the radiant energy of the sun, and it evaporates ices from its surface. And those ices evaporate into a very tenuous gas that dashes away and actually levitates fine dust from the surface too. So when a comet is active, it produces a dust tail and a gas tail. The gas tail streams outward from the sun, swept by the solar wind. The dust trail follows a separate path, and sometimes you'll see photographs of comets that show two distinctly different tails. One's a dust tail, one's a gas tail. But the theoretical studies of the evolution of short-period comets have shown that if a short-period comet goes through the inner solar system many times and gets baked many times, it will lose all the volatiles in its surface layer, leaving behind what's called a lag deposit, a left-behind dust deposit of black dust. Now what this does is very important. That dust is opaque. It blocks the penetration of sunlight into where the ices are, and it's also an absolutely lousy conductor of heat. So even if the surface gets quite warm, that heat is poorly conducted inward, and by the time that layer of dust is 1 to 10 meters thick, depending upon the orbit of the comet, depending upon who did the calculations, depending on their assumptions, 1 to 10 meters thick, that's enough to shut down the comet. Now it just happens that we have a comet that was discovered some years ago, Wilson-Harrington. Wilson-Harrington was seen and then disappeared. And quite a number of years later, an asteroid was discovered whose orbit, strangely enough, seemed to coincide perfectly with that of the missing comet, Wilson-Harrington. So what we have seen is a comet transforming itself into an asteroid. Should there be an impact of a piece of meteorite debris on that body which disturbs the dust layer, it could reactivate as a comet. Is it a comet? Is it an asteroid? I'll let you decide what to call it. I'll let a special commission of the IAU decide what to call it. By the way, if I am ever invited to serve on a nomenclature committee of the IAU, just shoot me. Thank you. So, 20% water, unless we're talking about an extinct comet core, in which case the thing may be 60% water ice. How hard is it to extract ice from dirt? Well, you can do it by vaporization, or you can do it by melting. Golly, this is getting complicated. We have two possibilities. But the ice is of extreme value as a propellant and also as a life support material. There are these two things that people like called water and air. Okay? The part of the air that you most appreciate is the oxygen. You only appreciate the nitrogen if you happen to be in an all-oxygen environment and strike a spark. Making air and water not only provides the consumables needed by astronauts, but it also provides the raw materials for space agriculture. What a novel idea. There have been a few little experiments involving growing plants on the Salyut space station some years ago, but small scale, just a demonstration of proof of concept, nothing more than that. Compare that to the moon. Solar wind concentration of hydrogen in the lunar regolith reaches a maximum of about 100 parts per million in the Mare basins, the dark basins on the near side of the moon, which have lots of the mineral ilmenite. If you don't know what ilmenite is, I'll leave it that way. No, it's an iron titanium oxide, FeTiO3. So some hydrogen gets trapped in there, and if you bake out that hydrogen, you get the water equivalent of 0.1% of water, assuming you have perfect recovery of the hydrogen. So a near-Earth asteroid that is vastly easier to get back from than the moon, and which contains, say, 20% water instead of 0.1% water max, is clearly an attractive resource. What you might ask about ice in the lunar poles: one, I have seen no guarantee that the concentrations and distributions of those deposits make them amenable for mining. They are in the bottom of permanently dark craters in the polar regions of the moon. The ambient temperatures are below 100 Kelvin, at which temperature virtually all metals are as brittle as glass. What are you going to dig with? It'd be very challenging indeed. I don't discount completely the possibility that someone will figure out a way to mine water at the lunar poles. But once you've done that, you're still at the bottom of the moon's gravity well. And you still need that large delta V to get off of it. Other attractive materials, metals. The M-type asteroids, what does M sound like? It sounds like metals. The M-type asteroids mostly, turns out some of them have been mischaracterized, but they're mostly metallic, iron-nickel alloys, similar to the iron meteorites that we have in our museum collections on Earth. They're about 99% ferrous metals. The chondritic meteorites. What's a chondrite? A chondrite is a primitive, that means truly ancient, unmelted sample of raw solar system solid material. The chondrites contain crustal material, like Earth's crust, mantle material, like Earth's mantle, core material, like Earth's core, but all homogeneously mixed together on the scale of millimeters. It's like putting Earth through a truly gigantic wearing blender and homogenizing it. So these chondrites contain as much iron, as large a proportion of iron as the Earth, but it's there as pieces of iron sitting there on the surface, not hidden in a core which is several thousand kilometers beneath your feet. And certainly on Earth, calling the Earth's core an ore would not be justified. Lunar regolith contains 0.1 to 0.5% of metal, most of which is fragments of asteroids that have hit the moon and suffered an ignominious debacle, to use polysyllabic nomenclature. They have blown themselves to bits, and most of the metal you see on the moon is asteroidal metal. There is some that is produced in situ by the shock heating of lunar surface rocks that contain iron oxide minerals, iron oxide bearing minerals, with implanted solar wind hydrogen in them. So during the impact, the violent heating event heats up the hydrogen and the oxygen together. They react to form water. So anyhow, the moon, just to put it in perspective, the average composition of the crust of the moon is very similar to the composition of slag. And slag is the material that we discard after metallurgical operations here on Earth. Now, I did not say that it's worthless. And I did not say that some clever person can't find a way to use it. I'm just saying you are starting out here in the very most unpromising and chemical environment you possibly could. Okay, I said we need simple and efficient processing schemes in order to qualify these materials as ores and not simply curiosities. We want to consume a minimal amount of energy per kilogram of product. We want the processes to operate without consumables that come from Earth. If you use any consumables in your process, it should be something that you make locally. These spacecraft should have, these processing plants, should have very few mechanical parts, because that's where your problems arise. You're operating with gritty dust. Every movement grinds something down. You want to minimize mechanical parts. You want modular design so that you can actually carry spares and effect replacement on orbit. You want the operation of these things to be highly autonomous. You want onboard artificial intelligence, expert systems programmed into them for process control, to identify problems, to say, oh, I know how to fix that problem, or to say, oh, I don't understand how to fix this problem. Maybe I'd better phone home and get some advice from the people who built me about what to do next. These little factories also should have a high degree of self-diagnosis and self-repair capabilities, which goes hand in hand with modular design. And they should make maximum use of direct solar radiation, low-grade solar radiation, not being highly dependent upon lots of electricity or upon a nuclear reactor. Solar power. They should use regenerative heat capture wherever possible. That means just using, capturing as much of your waste process heat as possible to preheat the stuff you're going to heat next. Okay? So it's just common sense from a chemical engineering standpoint. This is a very strange kind of chemical engineering here, in zero gravity in a hard vacuum. And then we have material. All right, fine. What do? We can process it mechanically. The crushing strengths of meteorites are well known. Many of them have been studied. The metals have crushing strengths of about 3.5 kilobars. How easy is it to crush a piece of stainless steel? Okay. The trouble with meteoritic iron-nickel alloy is that it is malleable, meaning if you crush it, it gets thinner and wider. It doesn't break apart readily. So crushing is sort of a misnomer here. You're flattening it more. Suppose you land on a metallic asteroid that is 30 kilometers in diameter, a single crystal of steel. What are you going to do with it? Okay. There is a great virtue to having regolith material, the surface material of an asteroid, pre-crushed and disaggregated by impact events. You don't have to pay for them, and you don't have to replace the equipment that gets busted trying to crush this stuff. The stony meteorites, the most common classes of meteorites, the ordinary chondrites, have crushing strengths ranging from 100 to about 2,000 bars, 2 kilobars. That's a pretty hard rock. The volatile-rich carbonaceous chondrites come in a variety, probably as many as 15 different flavors, which differ somewhat in their composition. One class of them, called the CM chondrites, has a crushing strength of about 10 to 100 bars, which means with a little hammer, you could easily tap on them and crush them. The CI chondrites have crushing strengths of 1 to 10 bars. You can take a piece of CI chondrite, most of them, put a piece between your thumb and forefinger and go like that and crush it. So crushing isn't always hard, depending on what you land on. Cometary meteors frequently have strengths less than 0.1 bars and sometimes down to 10 to the minus 4 bars, meaning they're, in many cases, about as strong as the stuff that you sweep out from under your bed. Very light, fluffy material with very little mechanical strength. The surface of an extinct comet core may very well be this fluffy material. And then finally, we have the Weibull strength law. The Weibull strength law says that the bigger the weaker. That's sort of counterintuitive, isn't it? Why should a bigger rock be weaker than a smaller rock? The reason is really actually very simple. It was derived mathematically before it was proved experimentally, but it's here it is. Rocks can have cracks in them. The bigger the rock, the more different scale sizes of cracks it can have in it. So the weaker it is. And this is indeed borne out in practice, and the Weibull strength law is very familiar to mining engineers and geologists who take advantage of it routinely. Then we have powder. What do we do with that powder to separate the minerals? We have various physical methods of beneficiating minerals. Beneficiating just means concentrating. Magnetic, electrostatic, density-dependent separation, which requires gravity or the moral equivalent thereof, artificial gravity produced by swinging it around, and volatility. As a chemist, I almost hesitate to mention that volatility is a physical trait. I prefer to think of it as chemical, but that's okay. Now, here are some examples of specific processing schemes that can be brought to bear. Ice extraction by melting and sublimation of native ice using solar or nuclear power. I put nuclear power in there because there's always people who ask, what about nuclear reactors? But I prefer solar power. I mean, we have there a wonderful example of nuclear reactions providing us free energy, okay? So why not use it? Okay, once you get the ice out, what next? Well, most of the water in the carbonaceous meteorites is chemically bound. It's in the form of clay minerals. There are hydroxyl groups in the clay minerals. There's interlayer water between the layers in the clay minerals. Picture mica. Have you ever peeled a piece of mica apart into layers? There's interlayer water between those layers. There's these CI chondrites contain hydrated salts like gypsum, epsomite. So if you heat these materials up to a few hundred degrees Celsius, they will spontaneously release their water. So we can do that by solar or nuclear heating. Then we can electrolyze the water into hydrogen and oxygen. What do you need for that? Well, you need energy. Where do you get the energy? How about sunlight? How about using the sun as the source of energy? Photovoltaic cells, okay? Liquefy the hydrogen and oxygen, and you have the fuel needed to build your own Saturn V or space shuttle. Not that I would particularly recommend either of those models, but it gives you an idea of the utility of hydrogen and oxygen as rocket propellants. Very, very high performance. Then for the ferrous metals, there is a wonderful scheme which has been the source of most of the world's production of nickel and a lot of the cobalt too for many years, called the gaseous Mond process. Mond being the name of the scientist, Ludwig Mond, who's a German chemist who discovered this back about the year 1900. And it's been in commercial use since about 1905. If you have a Canadian nickel, the nickel in that nickel has been through the Mond process. That's how it's processed. That's how it's extracted and purified. Here's what happens. You take a native alloy, like an iron meteorite, and you expose it to carbon monoxide gas at a pressure of about 100 atmospheres and a temperature 100 to 200 degrees Celsius. Very normal temperatures, very easily attained temperatures. 100 atmospheres pressure of carbon monoxide, and what happens? The iron and the nickel turn into gases. This is commercially used. This is not a fiction. This is not an idea. This is not a what if, okay? Iron reacts with 5 carbon monoxide molecules to make iron pentacarbonyl gas. Nickel reacts with 4 carbon monoxides to make nickel tetracarbonyl gas. These gases actually have about the same physical properties as water. They have about the same vapor pressure, or they're denser, but they have about the same freezing point, the same boiling point, the same vapor pressure. But they're different enough from each other so that you can easily separate the iron and nickel carbonyls from each other by distillation. So you can get pure iron carbonyl, pure nickel carbonyl. The iron carbonyl can be made with extremely high purity. Those of you who have taken analytical chemistry have undoubtedly seen a black powder which is called analytical grade iron. It has a purity of 6 nines, 99.9999%. The only way to make 6 nines iron is from the thermal decomposition of iron pentacarbonyl. That stuff is very interesting. Let's say you make a wire out of it. That wire has a tensile strength which is 5 times as high as piano wire. Very, very high strength, very high tensile strengths. Another interesting thing, let's suppose you make a bracket, a fixture, a bolt out of this iron, and you put it in a terrestrial environment, that iron is so pure that it has the corrosion resistance of the best stainless steel. It is not iron that corrodes. It is the defects in the iron that let it corrode. And when you get down to 1 part per million of impurities or less, so few of those defects are exposed at the surface that the iron really doesn't even notice it. So 6-9's iron. Chemists call it high purity iron. Engineers strangely call it high pure iron, suggesting that instruction in the English language would be beneficial for at least some of that subset of humanity. All right, so how much is there out there in the near-Earth asteroids? Are we talking about a little bit, a lot, or a truly enormous amount? The total mass of the near-Earth asteroids is about 120 times 10 to the 18th grams. 10 to the 18th grams is not something that you normally think about, so it's 1 trillion tons. So we're talking about 120 trillion tons of mass in the near-Earth population. Divide that by the number of people on Earth, and you see that we're talking here about large amounts of matter. Tens of tons for each person on Earth. 40 times 10 to the 18th grams, 40 trillion tons of ferrous metals. About 2 trillion tons of water. This is a huge amount. And then we have these the metals that are present in that M-class asteroid, or that metallic meteorite that we have in our museum collections. We can say, we can calculate now what the Earth surface market value of those metals would be. Now here we have a metal alloy that has typically 7% nickel, 0.5% cobalt, and it has tens of parts per million of platinum group metals in it. So let's just say, take that amount of iron that's in the near-Earth asteroids, multiply it out times its Earth surface market value, and that's what it's worth at the surface of the Earth. Let's see, $11,000 trillion. That would be $11 quadrillion. That's even bigger than the national debt. Well, maybe not next year, but still, $11 quadrillion. The nickel is worth about $70 quadrillion. Don't throw away the nickel. The cobalt is worth, what's this? The same number, $70,000 trillion. The platinum group metals, 70,000 trillion. What's going on here? The prices of metals on Earth depend on their rarity. Okay? So, having a body in which all the rare metals are not hidden in the core, but are uniformly mixed throughout, jumps them all back up. Those relative prices are determined by the rarity on Earth's crust. But that's not the way they are in meteorites. All right? So that's a pretty good amount of money. How do you intend to make your first $1 trillion? I thought so. All right, let's suppose we bring them back to Earth. I have platinum group metal prices. I should have updated this. This was actually January of 2013. The prices are fairly volatile because they're subject to manipulation, and they're also volatile because of new commercial demands that arise unexpectedly for them. Things like producing LED lights, things like producing phosphors in television screens, things like producing corrosion resistance coatings, and so on. So the prices are pretty hefty. Those are the prices in US dollars per troy ounce. Why troy ounce? A troy ounce is about an ounce. It's about 31 grams. Okay, it's about an ounce. But people in the jewelry business have their own carats and sticks. So look at these prices. Like rhodium goes up to $7,000 an ounce, and an ounce of rhodium is about this big. These things have densities of 20, 22, 23 grams per cubic centimeter. So it doesn't take a lot. If you were to fill a space shuttle payload bay with this stuff, you'd never be able to move it. It's that simple. Okay, so what else can we import to Earth that's valuable? Energy, solar power. Why wait for the pitiful small fraction of solar energy that strikes the surface of the ground on the day side of the Earth when there are no clouds overhead? Why not just go out and bask in the sunlight 24 hours a day, facing the sun with your solar voltaic arrays, and then beam the power down to Earth? So energy is potentially a very huge issue here, solar power. And fusion fuel is a potential market too. It happens that the asteroids are a terrible source of helium-3 for fusion fuel. There's been a lot of talk about extracting helium-3 from the surface of the moon and bringing it back as a fusion fuel. Helium-3 deuterium fusion is quite clean, very low neutron yield. There's very little experience with it here on Earth. It's sometimes used experimentally during the test phase of a new fusion experimental reactor. So we don't have a working fusion reactor of any type here on Earth yet, not a power reactor. And I want to tell you an eternal truth. Commercial electric power generated by a fusion reactor is 30 years off. And I know that this is an eternal truth because it was true when I was an undergraduate, and it's still true.
Yeah, it's always 30 years.
Always 30 years off, yes. So maybe, maybe not. And there's also the issue that the fusion fuel, the helium-3 on the moon, to get 1 ton of it out, you need to process, bake out all of the solar wind helium-3 and plant it in 100 million tons of lunar dirt to get 1 ton of helium-3. 1 ton of helium-3 will run North America for a year, you know. But 100 million tons of moon dirt, this horrible stuff, gritty, full of glass fragments, highly abrasive, and sticky, yes, thanks to van der Waals forces. Many of us don't appreciate van der Waals, but he did a lot for us. Okay, and then we have nonmetals. Those very same metallic materials and meteorites that contain all of these interesting elements up here, plus the cobalt and nickel and iron, also contain, in solution in the metal, elements such as indium, gallium, germanium, arsenic, antimony, selenium, and so on, tellurium. They're not nearly as valuable. However, if you have a use for them in space, such as making, say, germanium solid-state devices or gallium arsenide solid-state devices, the materials to manufacture them are available right up there in space. And if you're processing the metals to make the framework of a solar power satellite, then somewhere you've got a bag full of platinum group metals, you know what to do with that, and you've got a bag full of semiconductor elements. So think about it. Now I'm going to talk about a thing called demandite. Who knows what demandite is? Yes. Yes. Demandite is the list of all the things that you have to provide in order to support civilization. It is the recipe for maintaining a healthy civilization. The unit of demandite is the amount of resources that must be in circulation to support one person for life. And I will specify here that we're going to be talking about an economy in space in which you're going to be using solar energy to power the recycling, and the recycling will be done scrupulously. There will be no dumps. The dumps of today will be the mines of today. Okay? Recycling. Okay, then the near-Earth population contains 80 billion units of demandite. Using solar power, the near-Earth asteroids could sustain a population of 80 billion people from now until the sun dies of old age. If you're interested in long-term investments, well, enough of that. And the asteroid belt contains about 100,000 times as much material as the near-Earth asteroid population. Here it is. Here's a breakdown here. This is what's available in the near-Earth asteroids. This is the amount of inventory of each of these materials per person. Let's see, carbon, 1 million grams. That's a ton of carbon per person. Now let's see, the carbon in your body, a few kilograms of carbon in your body. Then you want to have lots of plants, and you want the plants to regenerate the air and grow your food. So let's set aside 100 times the amount that you need for yourself for plants. Even if you can't eat them, even if you can't process them into biofuels or whatever, you can still appreciate them. I would be growing dahlias up there, I'll tell you that frankly. But you go down the list here and you say, what population would be sustainable? And the numbers are all bigger than 80 billion, but not much bigger. And in fact, some of them look a little bit tight, like for example, cement. Well, it's not really cement you want. Cement on Earth is used for building construction. Cement has a poor tensile strength. It has an excellent compressive strength. Would you like to live in a habitat in space that has poor tensile strength? Any volunteers? We need, the Bigelow Company and I have an experiment in mind. So it's actually calcium oxide for industrial uses that we need. We need enough calcium for the calcium phosphate in our bones. We need enough calcium to keep our plants happy. We need enough calcium so that our ducks will lay good eggs with actual shells on them. If you've ever seen an egg laid by a chicken which has no shell on it, it's exactly as messy as you think. But it does happen. So calcium, we need calcium in circulation, mostly for industrial uses. So that's not too bad. Actually, if we think of it in terms of calcium oxide, we're fine. If we think in terms of cement, we've got a problem. Phosphates. Well, this is based on terrestrial use of phosphates as fertilizers. And how do we use them? Well, if a little fertilizer is good, a lot more would be better. So we'll just throw a few extra tons on this acre and let it end up in the Gulf of Mexico. We don't need to waste it like that. In a closed ecological system, any phosphate that's not used by the plant on the first pass will be used on the second pass. Right? So I'm saying, let's say that we're 10 times as efficient. I think we could actually be several thousand times as efficient. But let's say we're 10 times efficient. So that's not a limiting factor. Water, 500. Oh, that's 500 billion people. That's pretty good. Nitrogen, 400. Now, nitrogen's an interesting issue because you need nitrogen first and foremost for fire suppression. You need to dilute down that oxygen in the air at least 2.5 or 3 to 1, and preferably a little more, in order to be safe from very rapidly propagating fires. An iron nail will burn in pure oxygen. Okay, so you want to be very careful about that. So you need the nitrogen for that, and you need nitrogen as nutrients. You need the nitrogen for the amino acids and the organic bases in your body, and all the plants need it similarly. So I suspect that overall, the limiting material for human expansion in space may well be nitrogen. There aren't an awful lot of accessible bodies with nitrogen-rich atmospheres out there. Mars has a far, far lower nitrogen inventory than Earth. Venus has lots of nitrogen, but it's at the bottom of a deep gravity well. And hey, folks, we are trying to kick off the surly bonds of Earth and go out there and feast off the land without having to hold our nose and dive into a hellish atmosphere to retrieve nitrogen. High utility products for use in space, high purity iron. high precision chemical vapor deposition of nickel in molds, and by means of laser chemical vapor deposition plating. So you can build up by means of three-dimensional plating, 3D printing, complex objects, many of which would be very, very hard to make or machine on Earth because of their complexity. But you can grow them out of a vapor by clever use of a mold or of a laser. Bulk radiation shielding. Wherever you go in space, there's radiation. Close to the sun, you need to worry about solar flare activity, high energy protons. Far from the sun, you need to worry about galactic cosmic rays. In fact, everywhere you need to worry about galactic cosmic rays. And you need several meters of rock shielding to protect you from them. Several meters. So when you go back to that previous slide, which talked about silicate availability, most of those silicates are not used internally. They are an outer shell around your habitat, the radiation shielding to protect you. You can use bulk regolith, you can use metals, you can use almost anything as shielding. The most efficient shielding against cosmic ray proton primaries is hydrogen. You don't want to surround yourself with a tank of liquid hydrogen, you would quickly freeze. You want to surround yourself with a tank of water, or of ice, or of paraffin, or of a light hydrocarbon. There are more hydrogen atoms per cubic centimeter in liquid methane than there are in liquid hydrogen. So, yeah, you want hydrogen. And where do you get the hydrogen? You get it from water. Where do you get the water? You get it from carbonaceous asteroids. Now let's talk about metals. I'm going to talk here about 1986 DA, the smallest known M-type asteroid, about 2,300 meters in diameter. It contains about 40 times the amount of metals mined over the entire history of the human race. It contains 40 billion tons of iron, 7 tons for each person on Earth. This is one small M-class asteroid, one NEA, the smallest known metallic asteroid. What if it turns out that this isn't metallic? Well, then it means that the smallest known metallic asteroid is actually bigger than this, okay? It contains over 1 million tons of platinum group metals with an Earth surface market value of about $100 trillion. I don't think anyone would be idiotic enough to bring it all back. I mean, who would want to crash the market? So you trickle it back. I like to, it's an investment opportunity. Now, where are these materials likely to be in demand? In low Earth orbit, anything outbound passes through low Earth orbit, doesn't always stop there, but it passes through it. Propellants for geosynchronous transfer orbit, getting from a space station orbit out to geosynchronous orbit. Station keeping in geosynchronous orbit. Missions to the moon. Wouldn't that be ironic if the cheapest way to get to the moon was to bring water back from a near-Earth asteroid and bring it to low Earth orbit and use it to... Okay. So that you could go to the moon and mine ice. And if you're going to Mars, you need a heck of a lot of propellants. The moons of Mars, Phobos and Deimos, are as dark as carbonaceous asteroids, but they don't show signs of water in their spectrum. We think we know why that is. I'd love to see what the interior of them's made out of. I think there might be some nice water in there somewhere. Space station also needs radiation shielding. And then out in geosynchronous orbit, we have structural metals for building solar power satellites and anything else you need to build out there, station keeping propellants, and you can make photovoltaics for building solar power satellites. So those are some points of demand right there. Water can be used directly as a propellant. It doesn't have to be electrolyzed and processed. Imagine a big solar collector, a parabolic oven, if you will, that focuses sunlight upon a little thrust chamber here. And we trickle water into that thrust chamber. the solar energy, let's say we use rhenium metal as the thrust chamber. I know how to provide that, by the way. But let's suppose we use a rhenium thrust chamber. We can heat it white hot so that the exhaust of water vapor coming out of that engine actually isn't water vapor anymore. It's atoms of hydrogen and oxygen. You get a specific impulse of 1,000 seconds, for those of you who care about such things. It's a far more energetic than any chemical propellant. So this solar thermal propulsion uses only sunlight and water. Or you could use a nuclear reactor. Then we have electrolysis of water to make hydrogen and oxygen. We can use the hydrogen for solar thermal propulsion. Instead of running water into that thrust chamber, we run in hydrogen gas, right? That hydrogen gas will now come out of there as hydrogen atoms. It will have a efficiency as a fuel, a specific impulse, comparable to an ion engine. I mean, it's really tearing. So these are enormously efficient and promising propulsion systems. And then N stands for what? Nuclear? Yeah. And then we have hydrogen, oxygen, chemical propulsion, which takes us right back to the Saturn V. Okay, so what kind of asteroid should we look for? I think if there's any conclusion I'd like to argue very strongly for, it is that we need water. The C-type chondrites also contain 6% by weight of organic polymers, including nitrogen atoms in the polymers. So those carbonaceous meteorites and the carbonaceous and the C-type and related spectral types of asteroids, I've listed C, D, and P up here, but there's some others as well. They'll contain at least 10 to 20% water in the good ones, the CI types, and perhaps 40% total volatiles if you count hydrogen, carbon, nitrogen, oxygen, sulfur, and chlorine. 40% of volatile material you can get out of them. And that residue of 60% that you leave behind, 1/3 of that 60% is iron and nickel. So don't throw it out, especially if it has impurities in it. Okay, extinct short period comet cores are very desirable. They may be up to 85% total volatiles, counting 60% water ice. However, cometary cores are biased in favor of high eccentricity orbits. That means that they're energetically difficult to get to. Some of them are of intermediate accessibility. They're still a little expensive to get to, but they are so rich in the stuff you want that you may be very willing to swallow that, especially since that the body that you're going to is going to provide you the propellant to get home. Okay? 1977 VA is a type example of one that has interesting logistics. So I talked about how the evolution of these comet cores can leave behind a lag dust deposit. That dust itself is just black dust, but it's a mixture of organic polymers and magnetite. Can you think of anything to do with that? Magnetite is a wonderful iron ore in its own right. We know that the dust layers from these things are quite weak. The most desirable asteroids are very dark. They're very hard to discover and characterize using visible light detection techniques unless they are quite large. All right, let's suppose we have access to some near-Earth asteroids and we have installed some processing equipment on a few of these asteroids. The typical near-Earth asteroid has a perihelion, point of closest approach to the sun, that's quite close to Earth's orbit, and an aphelion in the heart of the asteroid belt. So your factory is going to go out and visit the asteroid belt once every few years, just in the course of doing its routine duties. There are near-Earth asteroids that have transfer orbits that graze Earth's orbit and graze Mars's orbit. They're pretty close right now to being transfer hotels for getting us from Earth to Mars. The radiation shielding you need could be provided by the regolith of that asteroid. The materials of that asteroid, the volatile materials, could be used as propellants. And you could essentially turn this asteroid into a traveling hotel, a traveling gas station, a traveling factory, and if mom and pop want to open a store on it, a colony. Would you want to live on an asteroid? I don't think so. Okay, all right, I got a deal for you. But what the asteroids are, they're not resorts, they're not vacation paradises, they're not even suburbs. They are raw materials out of which you can build whatever you want. So a base on a near-Earth asteroid gives you potentially easy access to Mars or to the asteroid belt. I've talked about the traveling gas stations and traveling hotels. Manned Mars missions can be run through their paces without ever getting deep in the gravity well of Mars by flying to a near-Earth asteroid and doing your rocket engine burn maneuvers in free space rather than deep inside the gravity of Mars, where, if something goes wrong, you will spend the rest of your life, which will not be very long. Phobos and Deimos are apparently former near-Earth asteroids that are parked in orbits around Mars. If you look closely at that picture, you'll see lines of tiny little craters on the surface. Let's see if I can point them out on here. Right down here. See these? Parallel striations. They're caused by the fact that a couple of big things have hit Phobos and excavated large craters and cracked the bedrock underneath. So we've got lots of cracks underneath a rubble and dusty layer on the surface, and the dust is trickling down into those cracks and making these crater chains. So it's quite possible that if you found the right place, you could rappel down into the interior of Phobos and explore the interior, the ultimate spelunking experience. Not only deep in a cave, but with no gravity. Hard vacuum. And did I bring enough air? I've compared the asteroids to the moon in a couple of ways. Let me just summarize that. Asteroids are relatively easy to get to outbound. In many, many cases, much easier to get back from than the moon. They are very rich and diverse in their resources. We have at least 50 classes of meteorites on Earth that derive from the near-Earth asteroids. So there are at least 50 different kinds of them, ranging from lake bottom mud, which is what the CI chondrites look like, to stainless steel. The strong points of the moon are the trip times are short. You can get out there and back in a week. Helium-3 recovery is a possibility, one that I don't happen to believe in, but I would be, I think, delinquent in my responsibility to you if I did not mention that there are serious people who think it's a real possibility. And lunar polar ice. Is it an ore, he asks skeptically. There is an important role for private enterprise in all of this, thus deep space industries and planetary resources. I'm not wearing a DSI shirt today, but please stand. Okay. The following message is brought to you by... The roles of private enterprise are multiple. Low cost, competitive access to space, meaning private launch services. It's happening before our eyes, and if you're not looking, it's happening behind your back, but it's happening. It's going on right now. Private enterprise can provide large-scale competitive mineral exploration. I, of course, wish DSI well, as the chief scientist of said organization, but I also wish our principal competitor well, too, because I think what we're seeing here is not two companies fighting it out, but we're seeing the birth of an enormous industry, an industry that will make all existing industries on Earth pale to insignificance eventually. Competitive resource exploitation. construction and operation of communication and transportation hubs and lunar refueling hubs too in select places. Private enterprise pays taxes. It doesn't spend them. We cannot afford a centrally controlled, duplication-free, government-dominated effort. We cannot afford it. This experiment has actually been tried in at least one other former country that I can think of. It was tried in China. They've abandoned it. Okay? And, you know, I get over to China once or twice a year, and I see what's happening over there. Every time I go, there are changes. Most rapidly changing country in the world. I was over there at the time of the last Party Congress when they retired the very last members of the Politburo and Central Committee who remembered the Long March. They're gone. They were replaced with Shanghai businessmen who are people who are dependent for their livelihood upon having good trade relations with the West. I cannot speak with such internal knowledge or personal knowledge about the People's Liberation Army. But I think it's safe to say that politically they're at the opposite end of the spectrum. There's a great potential for instability in that country and enormous promise as well. Okay, so enough of that aside here. Now let's go back in time. We are right here. We are the bow wave of the future. We are the ones who are forging on into the future and coming up with brand new ideas, right? All right, let's go back to 1903, Konstantin Tsiolkovsii. He proposed in 1903 a series of kinds of rocket engine tests that should be carried out to develop rockets. Single-stage rocket flights, multi-stage rocket flights, unmanned orbital flights. Look at the years in which they were accomplished here. Manned orbital flight, 1961, Yuri Gagarin. Prolonged manned orbital flight, 1965. Experimental air recycling using plants. This has actually been done on such a small scale that it wasn't really air recycling. It was just growing a few plants. So I don't really give that one credit. Spacesuits developed for use outside of spacecraft, done in 1965. Space agriculture to provide food for the people who are up there. Earth orbiting space colonies. Sounds like Jerry O'Neill. Use of solar energy for transportation and power in space. First application was solar electric propulsion, starting in 1965 with the first orbital tests of ion engines. Okay? Exploitation of asteroid resources is Tsiolkovsky's point number 12, writing in 1903. He saw the resources of the asteroids as being the body of resources that would liberate mankind from Earth. Number 13, space industrialization, the migration of almost all heavy industry into space. And number 14, the perfection of mankind and society, which so far as I can tell, hasn't quite happened yet. It may have to wait for numbers 12 and 13 before it will happen. My conclusion, there has been no real progress since 1965. H.G. Wells said, "There's no way back into the past. The choice is the universe or nothing." Collapse, introversion, exhaustion of limited Earth surface resources. And William Jennings Bryan, hardly a prophet of the space age, says, "Destiny is not a matter of chance, it is a matter of choice. It is not a thing to be waited for, it is a thing to be achieved." So our job is cut out for us. Going on to the asteroids, what can we do next? Well, we can do basic science, dynamical, physical, and chemical characterization of the asteroids, trying to understand their history, their evolution, where they came from, and where they're going. Planetary defense, need to understand the properties of the asteroids, their strength, breakup behavior, their response to attempts to deflect their orbits, and so on, which has, of course, enormous political overtones. Resource use, the need to practice large-scale mining, beneficiation, and processing of asteroid materials for commercial purposes. So these are what are going to be driving us in our choice of future asteroid missions. The next asteroid mission up for funding is the Keck Institute proposal to retrieve a near-Earth asteroid, a small near-Earth asteroid that would roughly fit in this room, and bring it back and put it into orbit around the moon, where, if you lose control of it, it will fall on the moon, not on the Earth. All of the asteroids that are targets for this have orbits that are quite close to Earth, and you really don't want to wait until they decide to land on a planet, because the planet that they cross is Earth. So the thrust here is to capture and return a threatening several hundred-ton near-Earth asteroid to a safe orbit around the moon using existing technology, just scaled up. It would exercise and demonstrate the capture and deflection technologies we need to defend Earth from errant asteroids. And it provides a real asteroid to serve as an international research park for both scientific and commercial purposes. There have been, I'm out of time, so I'd better trash this one, but there are all kinds of logistical studies about how to develop a space architecture that's based on the near-Earth asteroids, and this summarizes some of the conclusions of those studies. Okay? We are sitting here on the surface of a planet that has finite surface resources. We know that. We keep hearing, not a month goes by that we don't hear about such and such a material will be exhausted in X years. Well, of course, it won't be exhausted. What will happen is you'll have to move to much lower grade ores, which means the price is going to go through the roof. And you do that for a few commodities, and before you know it, you've got serious, serious economic problems. Any civilization as advanced as ours has to decide whether to move into space. Remember, H.G. Wells' choice. Mining asteroids increases the resources available to human society by about a factor of 1 million. The near-Earth asteroids will give you access to the asteroid belt. There, you make some fuel. You provide a few kilometers per second to hop off and rendezvous with a non-near-Earth asteroid, a belt asteroid. And from there, you can diffuse outward. So access to the belt follows almost automatically from having access to the near-Earth asteroids. From the belt, access to the satellites, the outer satellites of Jupiter and the Trojan asteroids is relatively straightforward. And that provides another huge increase in resources, depending upon how large a satellite you think you can handle and process and utilize. Growing civilizations, expanding civilizations are outward directed. They don't spend all of their time staring at their navels and contemplating their own eventual demise. They're outward directed, and they are the civilizations that are most likely to communicate. So when you're thinking in terms of interstellar communication, by far the most likely ones to communicate with us are those that have just undergone an immense expansion in their resource base, and they feel totally rich and want to do something truly spectacular and original. Some suggested reading here. This guy Lewis just writes and writes. Is this legal? George Washington International Law Review 2005, an article by two Lewises, one of whom is my son, who is a lawyer, but I still like him. So this is the change. We have to look beyond that little box, the Earth-Moon system, and we have to understand that space does not mean a government program. Space is the rest of the universe. It's the rest of the universe. The surface of Earth, so what if we run out of zirconium on the surface of the Earth? We have a universe out there. What's the most abundant chemical compound in the universe? Water. Oh well. What's the most abundant metal? Iron, yeah. Okay. If we don't do it, somebody will. And this is a summary of the asteroid belt's resources. Over here, the population sustainable by the resources of the belt using solar power for recycling. That's the number of people that could be supported. Let's look at nitrogen. This very small number down here. Only 14 million billion people. 10 to the 16th people. 1 million times the ultimate carrying capacity of Earth. And that's just the asteroid belt, which gives us access to the outer solar system. Okay, that's all I wanted to say to you. And I just encourage you to interest yourself in this issue. Pay attention to what's going on. And think in terms of the long-term future of mankind. Listening to the evening news, it's very hard to look beyond the next presidential election, which always seems to be just around the corner. But think in terms of the long-term future before us. We need to get ourselves out of a situation where one cosmic accident could wipe out the entire human race. And we need to be intelligent about it. So carry on, and those of you who are significantly younger than I am, I'm going to leave it in your hands.
John, do you want to stand there so we can see you on the camera? And I'm also going to grill you with the first question. What's the origin of the metal asteroids? How did they come to be so abundant in metals? What's our thinking on
the ones that we see as monolithic pieces of iron are, for the most part, probably the cores of larger asteroids that melted and differentiated, separated to form a crust and a mantle and a core, lost their volatiles into space, and then were pummeled by generations of further impacts that eroded the silicates off of their surfaces. By analogy to Earth, there should be the more or less pure iron nickel materials like the Earth's inner core, and then there should be metal sulfide materials. We've actually only got one meteorite in that category. It's called Soroti from Africa, which is about 50% sulfides and 50% metal. And I think there's a good reason we don't have more of them, which is that the iron sulfides are brittle as glass. So if you break them apart, they shatter completely. Then we have a whole bunch of asteroids that look like basalts. They look like mantle rocks. They look like olivine. These are the achondritic meteorites. And then we have crustal materials, and we have some classes of meteorites that look like crustal materials too, with very high abundances of feldspars in them, and sodium, potassium, aluminum, and so on, like crustal material on Earth. So most of those huge pieces of iron are probably cores of bodies that were big enough to differentiate. And how do you differentiate a 100-kilometer sized object? Long-lived radionuclides won't do it. You either need to have an admixture of short-lived radionuclides that will cook it violently for 10 million years or so, or you need to have heating by the early solar wind of the sun. We know that the early sun emitted a solar wind that was thousands of times denser than the present solar wind, and dragging that solar wind through an asteroid induces currents in it. You're dragging a magnetic field through a weak conductor, so you're inducing currents in it which will heat it up. So those are the two principal mechanisms for melting irons. And then there are other pieces of iron which could be made more locally at shallower depth by surface melting of an asteroid. They aren't necessarily pieces of cores.
Hello. I have a ton of scientific questions, but I'm going to ask you a philosophical question. Speaking of Tsiolkovskii's 14th point, I think anyone who yeah, Tsiolkovsii, thank you. I tried to pronounce it, but it had a lot of consonants in it.
By the way, I have a commercial venture you may be interested in, which is to establish a trade between Poland and Finland with vowels flowing southward and consonants flowing northward.
Just don't go through Wales or they'll snatch them all. So I think we can all figure, ways that greedy, short-sighted human beings could screw up space resources. Not the least of which is towing a small asteroid into near-Earth orbit and dumping it on a city you don't like, or things like that.
Which, by the way, is vastly harder and more expensive than dropping a nuke on it.
Well, yeah, okay, that's comforting, actually. But my question is, so how much do you think we need to grow up as a species instead of being, say, what Carl Sagan described as adolescent, before it's to our benefit to really do this on a big scale, as opposed to like a potential benefit and a potential huge risk?
I think that there is a large part of us that is still hunter-gatherer. And the urbanization is something that occurred rather late in human history. You don't have to go back too many centuries to find that every country on Earth was largely rural. So there's also what we think of as the American appeal of the frontier. If you go around and look at the many cultures around the world, I think you'll find that it's actually quite a widespread phenomenon. That America, in fact, was populated not by Americans, but by people from many, many other countries who had that impetus to go out and explore and innovate and expand the frontiers, to go where no man had gone before, or woman either, for that matter. So, yeah, some degree of maturation would be highly desirable. I've been telling my children this for years, and I'm telling my grandchildren this, and it eventually sinks in. By the time they're 70 or so, they're usually grown up. Just to let you know, in our family, we have a specific piece of terminology that we use here. We don't talk about the teenage years, we talk about the awkward years. And the awkward years are from 12 to 35.
Question over here. I heard that asteroids have been getting a bad rap in DC and in Congress, and I wondered who's behind the mudslinging against asteroids, and is it a logical argument, or is it just another pet project that they want funded instead? And also, if you could talk about the health of NASA's asteroid initiative, given that Laurie's no longer with us.
Mm-hmm. Yeah, well, there of course will be enormous pressures brought to bear on both sides of this argument. This is essentially a proposal for a change in the style in which humanity operates. Everyone who owns an ox will be afraid of it being gored. If you're De Beers, you'll be worried about somebody finding diamonds out there. If you're Inco, you'll be worried about new sources of nickel. Or, if you're Inco, you can say, hey, we have the technology that you need to extract the nickel out there. Let's team on this. And that's the choice everyone has to make. Solar power satellites, where would the capital come from to build solar power satellites? From the fossil fuel industry, of course. Because they're in the energy business. And if this is the wave of energy of the future and will get those pesky environmental groups off their backs, okay, then teaming is the way to go. So everybody will have to make that decision. Am I with it or am I against it? And there will be a lot who will go either way. It's always been like that, always. When my ancestors were, many of them were religious refugees from France who fled to the Netherlands. They were landless. They had to leave everything and flee by night to get out of the country. Those who didn't were dead, right? So they got to the Netherlands, and Netherlands was sending out expeditions around the world. They said, how would you guys like to sign up for an expedition to the Americas? We're going to send you over there, and you're going to go there for an express economic purpose, which is to find the 17th century equivalent of platinum group metals, which was beaver pelts. And you're going to collect the beaver pelts and ship them back here. And then after you serve for 10 years, you will be released and you will be given free transportation back to Amsterdam. So my ancestors came over to New Amsterdam, and they found that there was wonderful farmland all up and down the Raritan River and the Hudson River valleys. And they said, well, we don't really have to go back to a country where A, we are aliens, B, They have the highest population density in Europe. C, all the land's already owned by somebody else. We could just stay here. Okay, so New Amsterdam became, the British saw what a success it was and took it, and it became New York. My 8th great-grandfather had a farm on the East River in Manhattan. On that location now stands the Secretariat of the United Nations. He sold out too early. But the vision of Europe at that time was, look, here's a source of resources. Let's go grab them and bring them home. They had no thought of settling North America. It wasn't their purpose. The Spanish approach was, look at all the gold over there. Let's grab it and bring it home. Oh, and by the way, let's convert the heathens while we're at it. So they had two purposes. But, here we have a new frontier where we can write the rules, where there are no people whose resources we are appropriating, no people that we are going to give diseases to or get diseases from. I needn't tell you what America's payback to Europe was, but that's... here is a wonderful opportunity. Huge quantities of resources. So much out there that in the near-Earth swarm alone, we can meet every foreseeable need of every country on Earth on a non-interference basis.
I had a question about what would be the best materials to build these space colonies from what we have available from the near-Earth asteroids? I mean, should we build them out of iron? Should we build them silicate, carbon, or some combination thereof?
The answer is yes.
Yes.
Yeah. What I would envision is that you would build the structure like think of it as a building. Okay, the structural framework of ferrous metal alloys, steel, with a layer of several meters of radiation shielding around the outside, which could be unprocessed dirt, or it could be something more carefully selected. Unprocessed dirt is nice because small meteoroids striking it will just make a little puff and it won't penetrate. If you had a bag of water out there, you'd worry about it getting punctured. But yeah, silicates on the outside, ferrous metal structures on the inside. And the water used liberally to produce a highly livable environment inside, a biologically rich environment. Not something designed in a NASA lab where they say, okay, we need the following 4 species. But something much more akin to, here's what the environment is going to be like in terms of temperature cycles and humidity, water availability, nitrogen content, so forth and so on. Let's do several experiments where we take a biome like that on Earth and transfer a huge bite of that biome to that space environment. And let it fight it out. Let those who will survive, and those who won't. And the species that survive become the basis of your economy.
The burned out comets, or temporarily burned out comets, are the most attractive, in my opinion. Hydrogen seems to be the limiting resource in most of these environments in near-Earth orbit. The comets that are no longer emitting gas are pretty much in inconvenient orbits. What would you say is the best one of that set?
1977 VA.
And what's the delta V in orbital eccentricity?
Unfortunately, I don't have that with me, but it is a moderate orbital eccentricity. There are natural mechanisms that could perturb an extinct short period comet nucleus into more favorable orbits. The problem is that we have such an incomplete inventory of these smaller bodies that we don't really know if there are any that are much more accessible. If we could characterize all of the ones down to 100 meters in diameter spectroscopically, then we might well have a good answer to that question. The logistic studies that I did not have time to summarize involved 1977 VA. So they were able to demonstrate over a 15-year mission duration, mass return to the vicinity of Earth of 100 to 1, 100 tons for each ton launched from Earth.
I was just wondering, how does the economics of developing extractive technologies on asteroids compare to the economics of developing more sophisticated extractive technologies to extract the same kind of thing from here on Earth?
Yeah,
assuming, say, the need for habitat restoration and dealing with legal issues and boundary issues, et cetera, et cetera.
Yeah, I think the conclusion I'm trying to put forward is that the resource development of space is to a large degree uncoupled from demands on the surface of the Earth, except for energy and platinum group metals. If you want iron in space, you have a choice. You either make it there or you launch it from Earth. And I have no doubt that making it there, since you have raw materials that are steel, that making it there will be far cheaper than launching it from the ground. I talked in terms of the Earth's surface market value of many different metals, okay? But you need to think about it from a completely different perspective. What is the in-space market value of a ton of iron? Well, you have to ask, what does it cost to put it there? And the answer to that is lots of bucks, lots of bucks. $1,000 a pint for water in low Earth orbit. Okay? So they're really largely uncoupled from each other. And if we could offload energy production from Earth, put it in space, that would do away with, well, coal mining, of course. It would do away with most petroleum pumping because there's a limited demand that would still need to be met for lubricants and you know, polymer feedstocks and things like that. You'd have to view that as being completely supplanted by an architecture that is outside of Earth's gravity and outside of Earth's economy, except for the energy that's being transmitted down to the ground. You could probably make those solar power satellites entirely out of non-terrestrial materials without having much industrial impact on Earth. And if you do away with the entire energy mining and transportation business on the surface of the Earth, you reduce the environmental impact of human presence on the Earth by an enormous amount. If your home were heated by electricity that was beamed down from a solar power satellite and not from a coal-fired station at the Four Corners plant in Arizona, it'd make a big difference in many, many different ways. So how do you improve habitat quality on Earth? Stop messing it up.
Okay, you haven't talked about artificial gravity. Is it worthwhile building structures in space that you could spin up for artificial
Absolutely.
Gravity?
Absolutely.
Or maybe we just forget humans out there and send out artificial intelligent machines, then that becomes the
I wouldn't
new
want them
form
to
of
have
life.
that much fun, frankly. I mean, I'd be jealous. Yeah, definitely rotation is the key. Artificial gravity, what is it? It's not a machine that produces artificial gravity.
Yeah.
It's plain old inertia.
Yeah.
But inertia's been with us for a long time, and it's going to be with us for a long time. Might as well use it. And when I talked about density-dependent separations, that would require a spinning machine at the very least, if not a spinning factory.
Well, last question, and I'll encourage people who have more questions to go and talk to John after.
What do you project? You've talked about the asteroid belt and the Jovian moons and so on. What do you project as an energy source out there?
The amount of sunlight available is actually sufficient, but the efficient, it is. The typical point in the asteroid belt is 2.7 AU from Earth, so we're talking about roughly 5 times, 6 times lower solar intensity. So you need larger solar panels, yes. You also have the interesting issue of waste heat from the activities inside a habitat. So if you play it off carefully and look rigorously at your sources of energy and your heat emission from the surface, I think you can have both adequate electric power to run the machinery and reasonable internal temperatures at the same time. It's a trade study that has been done in a sort of a half-hearted way for several kinds of habitats. And I think I see the way clear to doing more elaborate ones. I'm not deeply concerned about that. If you take a look at essentially the cross-section of that belt covered by the asteroid belt around the sun, covering a fraction of a % of that with solar collectors is going to provide all the energy you need. And by the way, I should also mention, I keep saying negative things about nuclear reactors. In terms of meteorites and asteroids, there's not really any hope of finding decent uranium and thorium resources on any asteroids. Uranium and thorium deposits on Earth are the result of repeated cyclic reprocessing, hydrothermal reprocessing using water and air of terrestrial crustal minerals. It hasn't happened anywhere else. There may be some places on Mars where they might have gone to a small degree, but there's a little region on the moon called the creep deposits, potassium, rare earth elements, phosphorus. They're very feeble compared to anything we would consider mining on Earth. So I think basically we're going to have to make that mental transition from direct solar power to fusion power without the intervening step of messing with lots of uranium and thorium and their decay byproducts.
John, we have a special SETI Talks mug that's got some people on it, robots who've been through the metal transition that you're talking about. I'm sure they're built from asteroidal material and from the future. So please consider that when you're putting it up in your office.
Thank you. So any of my friends asked me where I was, I could say I went to Mountain View and got mugged.
Yeah, exactly. Fantastic. Please join me in thanking John. More duty, John, before answering everybody's questions. We want 2 correct answers. Now, I got the correct answer from John's blog. I may have misinterpreted, but the answer we're looking for is answer number C, letter C even. So hopefully we'll find one in here. There's a C, right? There's a C, okay. Cliff Winnig. And Bob Black. Okay. So we have two winners for tonight. Come and see me afterwards, and feel free to swamp John with more more questions about asteroids.